Hello, this is Carl Freund with Cambrian-AI Research. And today I have a very interesting topic I'd like to explore with you with the help of Joseph Soriaga, Qualcomm Technologies, Inc. He is a director of a senior director of technology there at Qualcomm. So Joseph, thanks for joining us.
Yeah, thanks for having us, Carl.
You bet. So I've been looking forward to this. I actually wrote a small paper with Joseph following a presentation you made where you really got into the whole bits and bits of on-device learning. And I think one of the frustrating things we've all encountered with our mobile devices is its an inability to learn continuously. Really detract from the experience where the digital assistant just doesn't understand what you said. Can you kind of explain why is that such a hard problem to solve, and how will on-device learning potentially change that in the future? And then afterwards, we'll talk about the techniques that you're exploring.
Yeah, sure. I completely relate to the example you're giving. Some of the key things that come together to to cause these annoyances. One of them is just that when we want to run models on device, we have these limitations to try to make them efficient and run low latency and so forth. And sometimes they may not, you can train them on a very big data set, but they may not actually have the capacity to cover these really large data sets. And so that may be, one of the aspects that they just don't reflect all the personal nuances of, each individual. Other limitations are that, not all the examples that occur that we want to train upon are going to be available when we build up our big training data set. And it's only through the interaction that we have more good examples or more personalizable examples upon which we can further fine-tune the model for each particular user. And so when we look at our research in on-device learning, that's exactly what we try to improve the models upon, is that for each of these cases that you kind of bring up, it's really we don't necessarily have to have the model learn every possible combination. They just have to focus on one user or one string of examples that are maybe more specific and then personalized to that. And so it makes sense to be able to do that locally, to have a lot of the examples captured when they're relevant, keep them local, keep them private, and then update the model so that they can be more effective and then still be very efficient to run on device.
Yeah, I mean, we always think of the learning process taking place in a large cloud with racks and racks of GPUs. Being able to do that on a mobile device, battery powered device, whether it's a phone or a factory or a street lamp, I mean, that's going to be a real challenge. What techniques are you exploring that would enable this kind of on-device learning?
Yeah, that's a great question. And indeed, when you think about phones and lampposts and all sorts of constraints that can come up, those are important challenges. We like to think of our research along two major areas, which we had in our presentation. Like in the algorithmic side, we want to make sure the overall machine learning solution is going to be effective in the particular use cases. And we look at roughly kind of three big examples. One is few-shot learning, where you may have the ability to have a few examples that are very well labeled, either because you have user interaction or some other way to ensure that the labeling is accurate, or the examples that you're capturing are very useful to fine-tune upon. And then, the other side of it is maybe you can gather more data, but maybe they're not as well labeled because it's tedious to label them. And so this is more in the continuous learning realm. And there's also research that we do to look at how best do we um, trade that off, where we have a lot of examples, but we want to make sure that we're tuning the model the proper way in light of these examples being a little bit noisy. And then, finally, we have, once we can do all this local adaptation, we can look to orchestrate aggregating how each of these models has been updated to see if we can have a better global model. And this is like federated learning is what this kind of instantiation is. And then, what coming back to example of a use case. So, you talked about digital assistants. So one use case that we talked about in our presentation is actually, the starting point of this, where we have a wake word, where, you may speak a word like, hey, Snapdragon, and that's when the phone starts responding to start listening for a command. And, in the example we looked at, one important thing is that sometimes not all accents are well captured in the pre-trained data set. And to prove the accuracy, you could try to make a bigger data set and get more examples, or you could just capture some of those examples locally and then fine tune. And that's what the on-device learning research that we pursued. And we found that it was a very effective way to solve that problem. And it was also very efficient, because when you do have a larger data set, you also may need a larger model to actually capture that diversity. And it's a bit maybe unnecessary if you're just trying to personalize to one user. So in our alternate approach, we had a small model, and then we just fine-tuned to those outliers, and it turned out that we could run this algorithm across everyone, and the inliers got slightly better, and the outliers had like a significant gain, and they maybe were not represented well, or the data set, not good combinations of examples that could represent them well. So yeah, so that's some examples of how algorithmically we can improve that. And then one other important thing, when you talked about these constrained devices, our research focuses on how do we deal with these computational limitations. So to complement that algorithmic research. So for instance, in inference, we as a research group look a lot at quantization, and that has been really important to very efficient inference on device. And we can do the same thing on training side. The quantization can lead to simpler operations, can lead to lower bandwidth when we're looking at calculating the gradients and all the data exchange that happens for training on like batches. So, some of the research we showed, you can quantize, and there's some clever things you can do in managing that to really still maintain a good accuracy when calculating the gradients. And then some other things, you can look to have certain model architectures where you can have invertibility throughout the model, so that what happens is in normal backpropagation, where you have to do a forward pass, and then you have to store activations as you're computing the gradient in the backward pass. But if you have an invertible model, you can calculate some of these step by step and just have to go in a backward direction. And that helps to really reduce like the memory requirement for the device, as well as the bandwidth for data exchange on the device. It really can help both the cost and the power consumption. So yeah, so that's kind of a variety of the topics that we look at to try to do this technology.
Interesting. And for the audience, at the end, we will have a link and a URL to the paper and the presentation as well, so you can dive in a little deeper. So Joseph, am I understanding this correctly, or would you use a different quantization for the backward pass than the forward pass? Can you even take it to integer on the backward pass? Talk a little bit more about that.
Oh yeah, you would. It's more a matter of it's the same quantization, but ranges may need to be done carefully and maybe actually data specific or batch specific. So when we're doing the backward pass, what we had in our paper was there are ways to adapt the range that have a lot less intermediate calculation for figuring out what that range should be. And that reduction in intermediate calculations helps to, reduce the complexity, computation, and even the hardware footprint. So that's
Yeah.
generally what I'm more talking about. Otherwise,
Okay.
it's the same
Thanks.
message here. Yeah.
Okay. Thanks. That helps a lot. So what's next? What are you most excited about in your research realm of research search that will enable breakthroughs in on-device learning? And what do you hope to bring to the market through your product organizations that will really change the experience people have as they interact with their mobile devices?
Yeah, certainly. So, like for our team, we're more on the AI. We are Qualcomm AI research, so we don't quite tie into the product, but we do try to see what we can do on device through our own. We have our own full stack research team as well that can take prototype devices and then try to make modifications to demonstrate a certain technique all the way out to a real time in your hand demonstration. Um, what I would say what our group is really excited about is, and the goal of the presentation was to just get people thinking that you can start, you may be able to realize this on-device learning, and it's a different way of having a machine learning models and applications evolve, because a lot of what has been done to this point is really massive data collection and being able to train and effectively try to generalize upon that. And now, as we show more use cases and try to come up with the enhancements that can improve the feasibility and even demonstrate the feasibility, we hope it inspires more people to think about their different applications and their different use cases. This kind of a technology does require a bit more thought and careful study to making sure that it's deployed and effective, but it is something that we're seeing is becoming more feasible, and it's really something that can help another dimension for AI applications in the future. And I would just like to also add that it ties in well. Qualcomm has always been focused on what can we do at the edge with the mobile connected intelligent edge, and this is another big piece we see with local on-device learning, with potentially federating local updates throughout the network. And yeah, we hope that people also start understanding this, and we see more applications emerging.
Excellent, excellent. Well, as I said, we'll have the links to your excellent paper and presentation so that developers watching this can dive in a little bit deeper and understand some of the technology and anticipate how they will be able to take advantage of this technology as it moves through research and eventually into productization.
Yeah, certainly.
Excellent. Excellent. Well, thanks again, Joseph, for joining us today. I really appreciate it, and helping us all understand what the future is for on-device learning, thanks to the research being done at Qualcomm. So thanks again for your help. Pleasure to have you. I look forward to further conversations with you.
Yeah, it's a pleasure being here, and I'm glad our team was able to share a lot of the stuff that we're doing.
Yeah, me too. Me too. Thanks a lot. Take care, and we'll talk to you soon. Bye-bye.
Bye-bye.
Okay. I think that was much better.
Okay.